Thank you very much. Professor R.P. Singh is very kind enough to introduce me. And as usual, he is a Baba kind of person, so always give you the good feeling and good vibes. Okay, so good afternoon, everyone. I'll be just going from linear to nonlinear. Somebody said that when we are just transforming from linear to nonlinear. So since morning, we have been just going through the linear thing. So I'll be just talking about this nonlinear interaction and generation of structure beams. And as you can see, I'm just coming from a research institute where teaching is not that much done. So that's why today's morning you have seen people coming from academics. They are very good teachers. So I'll not be trying to teach you the things because I'll not be good at that. Perhaps they are the person. So I'll be just explaining some of the things what we have been just doing in last 10 years or so. And if you have any questions, I'll be happy to answer that. Okay, so I don't know whether you have been to my lab because we conduct some conference. It's an annual conference organized by students. Many of the students have already visited. But in case you have not, this is the virtual visit to the front gate of my lab. So this is what you will see when you go in person. And inside this lab, there are a bunch of very energetic and enthusiastic people. Those who stays in this attire most of the time, but occasionally when they are sober, they come to the lab with this attire and try to do something that I am just presenting today. Okay, and these are some of the collaborators, those who have helped over the years for this activity. In nutshell, what are the things we just do in PRL or in my group is basically just playing with different beams. It's a Gaussian beam of different energy levels, as Professor R.P. Singh was saying. Then we manipulate the spatial structure of the beam, study and characterize their structure, do the parametric interaction, taking the Gaussian beam or the structure beam, go to different domains, and generating new wavelengths, entanglement, and many other things. In quantum optics, some part we do recently. This is the glimpse about this one, about the quantum optics activities. What we have been doing in PRL is free space quantum communication, and then we have also, I'll cover some part of it, the interference of single photon. So if a single photon carry orbital angular momentum, whether you can just do the interference and see the vortex structure. And then we are also involved in payload development. That will be perhaps the first Indian payload going to space for quantum experiments. That is, and also we are involved in prototyping of the entangled photon source. This is the payload design, some structure, and these are the activity what we conducted with Space Application Center, ISRO, for free space communication, quantum communication, and video conferencing over a 300-meter distance. Okay, today all we are here, or at least I am here, because of this man who started the laser. So in 1960, Theodore Mannmann somehow built the first laser. And after that, the laser field has moved with its shape, power, energy, everything. From, if you see this one, this is basically the view plot is borrowed from Gerard Mourrou's presentation or the Wikipedia that he has. So you can see the first laser was in 1960. By 10 years, almost all the lasers were there. So everybody got that. Once the idea is there, so people just went other work, and then going to the key switching, mode locking, and then there is certain intensity they can reach before the starting of CPA, and you might be aware that a Nobel Prize was given for this, Professor Gerard Mourroux getting that. And after that, the energy has gone up like anything. And that has also helped us to explore different science due to this high intensity. And then size also changed drastically. So this is basically the National Ignition Facility of USA, where Theodore Mannmann is holding his laser. So you can just see the shape. So this facility is actually lying over 3 football ground, whereas his laser he is holding. So size and shape has changed drastically. Power has gone up, but one thing has not changed is this. Basically, you cannot get any wavelength you want for your application using a laser, because the gain medium are not available. So for that, the solution is basically a nonlinear optics. So this coherent radiation, you might be aware about these things. So these are the things what nowadays everybody use the laser, and nonlinear optics is something that has started right after the invention of laser. Nonlinear optics was there. So it's a Kerr effect, Pokel effect, or Brian O'Brien, he invented this Icaroscope using the saturation effect to see this in World War II. People are just bombing, keeping sun behind. So as a result of which you cannot really see the spacecraft or missile. So he invented this one where he used this nonlinear interaction or effect to see the object when there is a bright source behind. But nobody really thought about nonlinear optics that can give you new wavelengths. Okay, so then it starts after the invention of laser, the 1961. Franken demonstrate, and this is the starting of nonlinear optics or the experimental nonlinear optics. So he borrowed a laser, ruby laser, focused into a quartz crystal, and used a prism and recorded a photographic plate using wavelength separation, and then got that pump wavelength and then second harmonic generation, and he submitted to PRL, and then copy editor thought it's a dud, so he removed it, thinking that perhaps there is error in or dud in the photographic plate, but that, believe me, it was there somewhere. So that is what is basically starting of the nonlinear optics. So just to give slightly a little idea about what is nonlinear optics. So if you consider that atom and then this structure, so electron is orbiting, so dipole moment is 0 because there is no dipole moment. So if you put electric field or light is there, so then this dipole moment will be created, and you get the polarization out of this one. If that field is oscillating, so then you see that radiating dipole has the frequency same as that input frequency. So that is basically the linear domain. But if you increase this electric field, then in that case, you have to write all higher order terms of nonlinear terms. So basically in the chi2, chi3, chi4. And in practice, basically we don't see these effects because this quantity chi2, chi3, they are very small, very, very small. So if you just want to get the number, so it's a ratio will be 1 is to 10 to the minus 20, 12 is to minus 10 to the power 24, something like that one. So as a result of which, before the invention of laser, so if you want to really see something for this quantity or this parameter, then this field has to be very high. That's why before the invention of laser, it was impossible to get that effect. So, so I'll be just basically talking about the second order nonlinear interaction. There are third order nonlinear interaction, a lot of people do, but I'll be just focusing on this chi2 nonlinearity, where second harmonic generation, where two frequencies or two photons of same frequency add and generate a new frequency. Some frequency generation can be there, different frequency generation. These are the second order nonlinear processes. And then if you just put like this, then let's say two different frequencies passing to the nonlinear going to the nonlinear interaction, generate a new frequency, which will be energy, will be the difference between these interacting photons or interacting beams. So it's a difference frequency generation, optical parametric amplification. So you can amplify the weak signal in the presence of a strong pump to generate a higher intensity. So other way, you can also have that strong pump going to the nonlinear interaction and splitting the photon into two different frequencies. That is called optical parametric generation. Sorry. And if you just put this optical parametric generation inside a cavity, then it forms an optical parametric oscillator. So you can just create an oscillator and where you can just generate it as good as a layer. So you'll get the coherent radiation out of it. But here, this signal and idler is a by convention. So energy of the signal, this photon will be higher than the idler. So that's a convention not to worry about. So there are some equations that satisfy a couple amplitude equations. So those are the things you can just see, elementary basic nonlinear optics book. If you just go through that, you will get that thing. So, but what I want to draw your kind of attention is that the energy conservation, two conservation law are satisfied always. It's energy conservation, where the input energy has to be equal to the output energy. So it's a parametric process. The parameter of the system doesn't really affect. And since we are just dealing with different frequencies inside a medium, this normal dispersion will not allow it. So in that case, to get that higher conversion, we need to really match the momentum of the interacting beam. So it's a momentum conservation has to be done. And in ideal situation, we have to do this, but in practice, if it is close to zero, then we can get that. So again, when I was just talking about the structure beam, various structure beams we work on, it's a vortex beam, we have heard about that. There is another class of beam which is called hollow Gaussian beam, which is having the same special structure as the vortex, but the phase is a plane phase. There is no singularity involved in this one. There is another beam, which is an airy beam, which is having three peculiar properties, like it is non-diffracting, self-healing, and self-accelerating. So beam bends away. We also work with this perfect vortex in case of vortex beam, where you can see this, the size of the beam is increasing with the order, whereas in case of perfect vortex beam, so you can just make this size of the vortex and the order two independent quantities. So using this perfect vortex, you can just make a beam whose size doesn't depend upon the order. We have also we also work with the Bessel beam. Bessel beam is another interesting beam which is having not self-acceleration, it's having non-diffraction property. So if you block the beam, then the beam will heal itself like that biological cell. And it's also non-diffraction, so it maintains its shape over a long distance. Then we also work with this vector vortex beam. Professor Tarak was telling about the vector vortex beam, where the polarization singularity is there. I'll just come to these beams. Okay, and all these beams have their own applications, like various applications people have just reported, like optical trapping, tweezing, and manufacturing. Nowadays, people are just using, so for quantum communication or communication as such, people are just using also the structure beam. Then light sheet microscopy is something which recently came up, where people use different beams like Bessel beam or airy beam, and then super resolution microscopy also that people use this structure beam. So now question comes, how do you make that? The very simple way is you need a mode converter to convert the beam. That is very simple. So if you want a beam, any kind of beam if you want, let's say I want this kind of beam, let's say vortex beam, then I have to design the mode converter. And when the Gaussian beam passes through that, it converts into that beam, any one of that. Okay, so designing this mode converter itself is challenging and difficult. Or nowadays people have just used SLM, where you can easily do this through this digital holography. You can just make any kind of special structure you want to make. So once you have this kind of beam, let's say vortex beam, and you design that mode converter I was just talking about, it's a fork pattern. So if you have this beam passing through, Gaussian beam is passing through the fork, it creates a vortex beam. And then to verify it, so you again do this interference of that, and then see the technique, see the fork pattern back. So from here, seeing the fork pattern, we can say whether it's a vortex or not. And in PRL, Professor R.P. Singh has came up with an interesting idea. It's a very simple one. So if you want to see the vortex, whether it's a vortex beam or order of the beam, so you can just use a lens, a very simple lens, and then tilt it. And then on that focal plane, you will see the modes, separation in the modes, depending upon the order. So if the order is L, then you will have L plus one number of modes or spots present in that one. Okay. Alternatively, so this when we are just doing this SLM, it's good. Basically, just it's very, very flexible. You can just do anything you want. But unfortunately, SLM is a liquid crystal, so it cannot handle power. So if you have a laser, so it will get damaged. So in that case, since I'm just working with nonlinear optics, so I need power. So in that case, we have this spiral phase plate. So it's a commercially available kind of thing. So in the transverse plane, the thickness of the plate is varying. So when the Gaussian beam passes through it, then it forms a vortex, or this spiral phase plate nowadays one can have is up to order 4, so something like that. And so these are the steps going, so that for one round trip, the phase difference will come from 0 to 2 pi. Okay, so this is the helical phase, and we have, and this is basically mathematical formula. So just to for completeness, I'll just put that. So as you can see, here is this term. So it's just basically order dependent. That's why the size of the vortex or the beam increases when the order increases. So you can see from there. Okay. So any guess what is this? This is basically a vortex beam, and it is a total internal reflection in a lens. So you can clearly see it's a cylinder kind of thing. You can, if you're just seeing in the lab, you will see a cylinder kind of thing where no intensity is there. It's just a multiple reflection in a lens. Okay, so, okay, now I have said that one is a vortex you generate using a mode converter. But again, this mode converter or spiral SLM, whatever you do, whatever you use, it's a wavelength selective device. So you cannot really use it for different wavelengths. Now, if you design a mode converter at 1064, let's say any wavelength arbitrary, you cannot use it for other wavelength. So it's a very selective. So then we, sorry? Yes, sir. Yeah, it is in the lab. This one you are talking about? Yeah, it's in the lab. I think it came in OPN also. Some of our students send it to OPN, and there are some news also after for this that photograph. Okay, so then what we try to do, we just try to see this vortex beam. The photons carry orbital angular momentum, or OM is there. So we try to understand in nonlinear interaction when it's passing through the nonlinear crystal, what are the changes we expect. So this is basically just a schematic experimental setup. We use a laser. Don't go to entire detail. So I'm just follow the pointer. So just take that beam, and there is a spiral phase plate. We use that OM imprinting, and then it comes back. Then put another OM, and then send to the nonlinear crystal where we do the second harmonic generation. When you do the second harmonic generation, then these are the special intensity distribution of the pump beam for different orders. So we have just use the interference to find out that it's a fork pattern. You can see it's basically just telling that order is 3 or 6. But in case of SHG, when we do this pump photon is going through the nonlinear crystal. So we just see the doubling in the vortex order. So we start with 1, we see 2. For 3, 6, and 6, 12, something like that one, which is confirmed from this number of lobes. So here in this case, we will have 13 lobes. So I say that about this process is a energy conservation, momentum conservation, and then we just come up with the conservation that in the nonlinear interaction, we have also orbital angular momentum conservation. So we have to have that kind of conservation present in this process. So, but nonlinear interaction is basically an intensity dependent process. So you should go with a higher power. But as you can see, so intensity is basically power divided by area. So as you can see, when we are increasing the order of the vortex, then the size is increasing. So area is dropping. So then effective intensity required for the nonlinear interaction is going down. So we cannot really just get higher output power. So that is what it's shown. So this is the conversion efficiency with respect to the pump order. So you can see when Gaussian beam can give you conversion efficiency, single pass conversion efficiency, something around 30%, we expect something around 1 or 2% for higher order vortex. So that is basically due to the orbital, the size is playing the role. It's not, or since the size is increasing with the order, we cannot really differentiate these two parameters. We cannot say whether it's orbital angular momentum is playing any role in the conversion efficiency or not. So for that, what we did, we used a perfect vortex. As I said previously, this is the normal vortex. And then we try to, yes, sir.
Actually, in standard second harmonic generation, you have of this angle tuning or this temperature tuning for phase matching. So here you also you can use the same thing or same PPLN you can use.
Yeah, so same PPLN you use for because you can use basically it's a BBO crystal same. So if you are just giving a Gaussian beam, it will be a Gaussian beam. If you are going with a vortex beam, it will give you a vortex.
So it doesn't matter.
No, doesn't matter. Doesn't matter.
Same technology.
Same technique. So then we try to understand whether basically just this variation or drop in intensity is whether it's due to the OM or the size. So in that case, you have to just
And what about beam walk-off? If the size is getting bigger and bigger,
yes.
beam
So
walk-off effect will be very prominent.
yeah, so all those effects we have just incorporated in the nonlinear interaction. So when we are just using this because basically, just crystal length plays a role. Since we are just, so we selected the crystal length which will not give you the walk-off because we don't want that walk-off.
Don't go for temperature tuning.
We have in other experiments also we have that temperature tuning is a PPLN. So, but you see, we have selected because apart from this special walk-off, here basically we are just dealing with femtosecond laser. So temporal walk-off is more. So that's why you have to just go with a very thin crystal so that we don't have that effect. Otherwise, the interaction doesn't really happen because this beam. So those things we take care. And since the beam size is increasing in walk-off will be lower for higher order. So we try to eliminate this order and size so that we can see them differently. That's why we just gone for this perfect vortex whose equation looks like this one. You can see there is no R-dependent part present in this one. So in that case, when we are doing this nonlinear interaction, we try to understand what happens. So again, same experimental setup. So here we have just generated perfect vortex, which is imaged in the nonlinear crystal. Here I have just used that PPLN. This is the periodic pole crystal and in the temperature tuned. So in that case, when we are doing this frequency conversion and then separating the green and the pump and measuring the spatial structure, you can see here normal vortex looks like this, perfect vortex looks like this. Even the order is 6, the size remains unchanged. And in turn, in case of second,
Charge of the vortex.
yes, charge of the vortex, order of the vortex, we say. So SHG of this beam will have again that perfect vortex because perfect vortex is coming in that perfect vortex, and then you can see that it's a doubling is happening. 13 lobes or 7 lobes or 3 lobes is coming. But interestingly, when we are just trying to see the size of this beam for both the pump and SHG beam, in both the cases you can see that size remains unchanged. So it's a perfect vortex, and in that case the conversion efficiency remains unchanged. So it's not really playing any role of this orbital angular momentum because we have just fixed the size. Once size is fixed, then the conversion efficiency is fixed. That is what we have just seen. Okay, so here and previously we talked about this, just one pump photon having orbital angular momentum L, another pump photon coming orbital angular momentum L. They combine.
Which laser you are using? NDR or something?
It's a fiber laser. Now it's not working, dead. Okay, so I talked about this, just in SHG, 2 photons are combining. So 2 photons having 2 orbital angular momentum, they will add. Now, can we just subtract? That is the question. So like this, let's say if I go with a pump vortex of order L and another vortex with minus L charge, something like this, and then do the nonlinear interaction in the crystal, so what will happen? So what do we expect? Do we expect a Gaussian beam? Because in this case, if L and L cancels out, can we just get a Gaussian beam or not? So
in these conversions, polarization does not play any role.
we maintain that polarization because nonlinear interaction is very selective. So you have to fix the polarization depending upon the,
Phase matching.
yeah, otherwise you will not have phase
What
match.
kind of polarization?
It's just all vertical polarization in this case.
Linear polarization.
Linear polarization, so no circular polarization will be there. Actually, nonlinear crystal behaves like a beam splitter. So you come with something, so they will always take the particular polarization. Rest of others will be unchanged and unaltered. So when you have a nonlinear crystal, then let's say we start with a pump beam, another pump beam is coming with their order different, and we are just doing that some frequency generation. So in this case, what we see again a donut intensity distribution. But the phase is basically, just plain. And you can understand, let's say you have dig a hole with a screw, right-handed screw. Now if you just try to put the left-handed screw in that one, then what will happen? You will be just removing the grooves. But the hole will stay there. You cannot really just fill the hole. So that is what is happening in case of light. It is also, one is rotating like this, another one is rotating, they combine. Then the intensity will not come back to the center to form a Gaussian beam. But if you So that is what we do. It's as a collinear. And if it is, this one is basically done in collinear geometry. It's as a collinear. So if it is a non-collinear, you have to see basically just over. Yeah, still there perhaps. But when we are basically just dealing with a non-collinear interaction of beam, so there is a very small narrow angle you have to, because otherwise it will not fall within the phase matching angle. So if it is there, but perhaps will be there. So, but what we are, just to make the life very simple, you just go with that collinear, and then SFG also, because we just start with a same pump beam, frequency double it, make a green, and then residual pump is coming, and then we are doing this some frequency generation in this nonlinear crystal and seeing their intensity. So you can see here we have for order 3 we get this kind of donut shape. Okay, so and that is called basically a hollow Gaussian beam, because there is no phase singularity present in this one.
Where are you considering every time L equal to 1?
Which started with L is equals to 3. L is equals to 3 or L is equals to 6 we started with. So this one is basically just this one input.
Why not L equal to 2?
If it is okay, so we have done till 6. So when we are just submitting the paper, so we have to go. No, so we cannot just put that one. But anything can happen. So I just say 2, 4, 5. Everything is there possible. For everything, it's true. But I was just showing few. So that's why I just selected 1, 2, 3. And this is basically just beam which is called hollow Gaussian beam. And if you Fourier transform it, it will it will give you a Gaussian shape, Gaussian intensity distribution with some radial index. Okay, so far we have just talked about, let's say, one photon coming, another photon coming, they are adding, and then you get something, just OM interaction is happening. Now, if we come with a single photon and they are interacting with the nonlinear crystal like this, so a pump photon comes to the nonlinear crystal, some interaction is happening, and then we generate 2 photons. Now, we talked about this OM momentum, OM conservation, momentum conservation, energy conservation. Okay, so all these things are known. Now, in this case, what will happen? Let's say if I come with an orbital angular momentum for the pump OM, and since OM is not divisible, let's say I go with 1. So in that case, the pump is having orbital angular momentum 1, then signal and idler is coming, so their orbital angular momentum sum has to be equal to the pump. So in that case, we will have 2 conditions, 2 situations can arise, something like this. Idler is not getting the OM, signal is getting the OM, or idler is getting the OM, signal is not getting, because I've just started with 1. It's not, you cannot divide. If it was 2, we can say that it's a 1, 1 is the division you can just make. Okay, so that is what we just tried with the OPG, optical parametric generation. In that case, we basically just see it's this is the pump OM modes, and that signal and idler. You can see this idler is having a Gaussian intensity distribution, elliptic, because you have just focused it to see whether there is OM content using a tinted lens. But in case of signal, there is lobe structure, but in this case Gaussian, because it's a Gaussian, that's why there is no change in the structure. So that means basically just OM mode of the pump is always transferred to the signal, not to the idler. Then we try to understand why it is so, and then can we just control it? Because can I selectively transfer it to the idler or the signal? So for that, we have designed something, just this experiment. It's an OPO, optical parametric oscillator. So we just take that OPO and then green beam, make a vortex, and then it's a doubly resonant optical parametric oscillator where signal and idler both are oscillating inside the cavity. But we have just put 2 arms for the signal and idler so that you can combine them and then again oscillating. So this is this part, up to this they are the common path, but then they have different path. So when we are just doing it, then we realize for pump, when it's a Gaussian beam, the signal is Gaussian, idler is Gaussian. So you can see from the interference pattern, it's always there. But when we go with, let's say pump is vortex order 1, then in that case also signal is 1, idler is 1, idler is 0. Okay. But why it's happening so? So then we just basically solve some dynamical equation and found that there is a condition for the transfer. So it's not that it's going to the signal or to the idler. Yes. Yeah. Yes. Yes. It's a frequency. It's going to the lower energy part. Okay. So what we realize, there is a condition. So let's say, because I said that the two conditions possible. Condition one is the OM is transferred to the signal, not the idler. So in that case, we calculate the threshold condition required for this. So you can see this is the formula. For other case, this is the condition for threshold. Now if you just compare, then this term and this term is the same, but the difference is the gamma S and gamma I. Gamma S, gamma I are the losses for the signal in idler in the cavity. So then we found that when the gamma S is more than the gamma I, or loss for the signal is more than the loss for idler, in that case pump will be transferred to the idler, or if it is the other way, then you can just transfer it to the signal. So basically, just inside the cavity, it's the loss decides which mode or which beam to take that take the OM. That is what we have just designed. So here we start with the orbital momentum 1, and in that case, when the loss for this is the red curve is the loss for the idler, so which is more than the signal loss. So in that case, we expect that the OM will be for the signal, that is what the signal wavelengths, and for in that case, the idler having a Gaussian beam. Whereas when we use output coupler and then try to increase the loss for the signal, the black line, while keeping the loss for idler the same, in that case, we can see it's a flipping. So it's basically signal is a Gaussian, idler is a vortex. Okay. Then we just try to use 2. So when we have 1, then we can say 1001, that is the state. When it's a 2, then it can be 2002 11. The 3 states are possible. So we just made that one. 11 is easily possible. Then 20 is something like that one, but for other one, it's very difficult to get experimentally. But we came to this conclusion, so the table, where you can see we have a control parameter that is basically the dynamically control of the loss inside the cavity. In that case, we can just create this output OM state, something like this one. So there is a control, so you just control the loss of the cavity. And then if you have n, ideally, means theoretically one can just get that one n plus 1 number of states using orbital angular momentum of n. Okay, so then we have just moved and then transfer that OM mode. Basically, just we have used this. You should appreciate this one. So from here, basically, we are just making an OPO. It's a single resonant optical parametric oscillator where we are just pumping the crystal with a single OM mode. Yes. Yeah, that's possible. So, but experimentally you cannot realize, because actually that is an infinite combination. It says infinite combination is possible, but you have to see that which one is having higher possibility gain. So basically, just 0011. Basically, that is, I have not said about the things why. Basically, in this process, it's just since you are just dealing with the cavity, it's just a mode overlap inside the cavity plays the role. So if you have that perfect overlap of the pump mode with the signal and idler mode inside the cavity, then that energy transfer will happen. Okay, so you can have n infinite minus 1 to get that conversion. But in that case, the overlap integral is very low. So we just calculate that overlapping integral and found that for a particular set, it happens. Otherwise, it will not. So even though all the possibilities are there, so your system doesn't allow. Like in case of here, so if you just go to this conversion, you start with this pump frequency. Ideally, you can get any combination of wavelengths. It's possible, but your process doesn't allow it. So it restricts, because your phase matching is restricting a particular set of wavelengths to present. Not everybody will be entertained. Okay. So then we start with a single OM, and then or single input, then use OPO and gone to all the wavelengths. Let's say you can just 10642, let's say this wavelength you can just see it's a idler wavelengths coming from 23 1, 0, and then signal wavelengths are like that one. So we have just try to go and then we tune. And in this case, basically what happens, so since we are making a cavity, so cavity plays a crucial role. Basically, when we are just talking about the cavity loves that fundamental mode to be there. Otherwise, it will not oscillate. So the gain for the fundamental mode is the highest. Then higher order modes will be there. But what is happening, let's say when the pump beam comes here, so in this case, idler is getting that OM mode, not the signal, because inside the cavity, Gaussian mode will first excite and then start overlapping with the pump and transferring it. So your gain, if you just keep on increasing the gain, perhaps higher order modes inside the cavity will come. But under these conditions, we always observe that one is the pump OM mode is transferred to the idler. So then what happens, you just start with a lower OM mode or a lower wavelength, OM mode at lower wavelength, and you can go to that mid-infrared. So this basically, just going to the mid-infrared, you can jack or you can transfer, where traditional mode converters are not present. Okay, so there are some of the wavelengths tuning, so you can just tune the wavelength and then go from, you can just see 3574 means 3 micron or 3.5 micron from just 2 micron, something like that, and so that all the way you can just tune these wavelengths. And since basically here we have just worked for the order 2, because these OPOs are very sensitive to the threshold, because that's why, so when we are just dealing with optical vortex order 1, the threshold is something like this one. So you can just go to 2, because the beam size is big, then the gain is low, then you have to, your threshold goes up. So that's why you cannot really just use this kind of system to generate higher order modes directly from the OPO, because the threshold is very high. And if you keep on you can you can have a very high power laser, you can put that entire power to this crystal, but you will damage the crystal. So that we didn't try. We tried to find out a way where instead of damaging thing or increasing the pump power, we try to check whether it's possible to go for higher order modes directly from that OPO. So here is basically we are talking about a dual crystal scheme, where OPO is designed. This crystal behaves like an OPO, and this crystal behaves like an OPA, optical parametric amplification. So the signal for this and this is the same, so we just maintain that. So in this case, we are just trying to make that OPO using the Gaussian beam. That's why you can see that Gaussian is coming, and signal is also a Gaussian beam, as you can see that from the signal. But we put another pump beam of the same wavelength in the second crystal, which interact with that Gaussian beam and transfer the vorticity or phase structure OM to the idler. So in that case, we can go up to order 6. So what I was just talking about, the difficulty in case of OPO, here using this scheme, you can just go to even order 6, and that too in the mid-infrared wavelength range. So that is what we are just talking about. So where we don't need to worry about the threshold condition. So you can see here that idler power for even the order 6, you can just go. And since basically I talked about only this vortex beam, but multiple beams are there. I have not really included some other beams using OPO, but I just covered only one experiment where you can see you can generate multiple beams directly from a single system. So you can just create an OPO, and from here you can see various beams. So this is basically the OPO, and we put some phase mask inside the cavity, pumping with the vortex beam and then playing with it. So if you do, then what we can see, so we are just starting with that vortex beam for the pump, then we can get a vortex beam for the idler, signal is a Gaussian, and signal can be also ARE beam, as I was saying, that ARE beam. So if you are just doing something to the cavity, so then it happens like this. So alternatively, if you are just trying to do some modification to the cavity, then in that case, signal is idler is vortex, signal is vortex. Signal can also have ARE vortex beam. So you can see it is ARE vortex beam, which is also confirmed from the intensity interference pattern. And you can just go for all the wavelengths wherever you want. and you can just control. So basically, just 3-4 kind of structure beam directly you can just generate using a single system. And when we are just talking about the airy beam, I was saying that self-healing property. So this is the airy beam, and some section of this beam is distorted or blocked. And if you let that beam to propagate, then it will come back to its original shape. And that is true for also vortex airy beam. So that is what we have just shown. And this airy beam is basically just having the width or central beam width remains unchanged. So the beam is non-diverging kind of thing, and then they have also self-acceleration. You can see is from the curve. Okay, so I'm just trying to touch some of the beams I'm just talking about. Another beam is a vessel beam. Vessel beam, many of you might be aware or worked with. So vessel beam is basically generated. Vessel beam is nothing but the superposition of infinite number of k values or k vectors. So if you have a beam which is having k vectors infinite, so if you let them interfere, then it forms a vessel beam. So how you generate? Basically using a Gaussian beam and then passing through Axicon. So Axicon is a device just like a lens. You just take a lens and then hold the center and then pull it out, whatever shape looks, that is basically the Axicon. So when you are doing it and then the Gaussian beam pass through, then it forms a vessel beam. But when you are making this Axicon, the problem comes because the sharp edge will be there at the tip. Tip of the Axicon is very difficult to handle. So that's why commercially available Axicons have here is a curved face instead of just as a angular face. Okay, and once you have that, the problems come there. So when you are just making the vessel beam, there will be intensity modulation in the beam. So when the beam is generated, due to this imperfection in the Axicon, the intensity distribution of the vessel beam will have some variation or modification. So then we try to understand whether we can just eliminate the effect of this tip of the Axicon. That is what we just do using a hollow Gaussian beam. And passing, since hollow Gaussian beam is having no intensity at the center of the beam, so it will eliminate the effect of this tip, and you will have a vessel beam. So this is basically the experimental scheme what we have just used, and then basically this setup is something more than the generation of vessel beam. We can just create 2 vessel beam, creating a potential oil kind of structure. That's why 2 arms are there, and we have generated. And then we try to study the nonlinear interaction of this vessel beam, and then seeing its effect in through the light matter interaction. So when you start with the Gaussian beam, as you can see, in case of Axicon, the intensity is having wiggling kind of structure. So this is basically not due to the imperfection of the Axicon, but basically this one is due to the scanning stage. So the scanning stage will be wobbling, and then you will see everywhere that is wobbling, that intensity modulation is there. But theoretically, you don't see this one. But when you see exactly the intensity distribution of this beam, in case of Gaussian beam, if we start with, then you can see that intensity variation is there, that purple color spots. Whereas when we are just using hollow Gaussian beam, then you don't see much. And another interesting thing is also the range of the vessel beam will be shortened and intensity goes up. So we started with the Gaussian beam, the range is very high, vessel beam lasts for longer distance. But in this case, vessel beam lasts a very short distance, but the intensity goes up. So that is what you can and get out of this one. So, and again, you can see also, let's say this intensity pattern is for hollow Gaussian beam order 3, and this one is for order 1. So if you just combine order 1 and order 3, then you can have a resultant intensity distribution like this combination of red and black curve. So that is basically just forming a potential oil kind of structure. Yes?
Usually in a regular lens, you have this underfilling, overfilling, and just filling kind of content, because depending on that, the focal characteristics will change. So do we have something similar here also?
We have not seen such kind of thing. Means basically this one is just.
You can derive the formula that it is there.
It's a kind of formula is there. So
How much of Axicon do you feel will decide on what
the range size will be, how much will be the size. Yeah, so a range of this one basically just as you can see here, so this section beam will be flipped this way, this section beam will flip this way. So that is the intersection domain, is that center domain. So if you have a underfield one, so the intersection domain will be small, so the Bessel beam range will be small.
No, it will be large, right? Delta Z will be large if the separation between the two rings is less.
No, I'm saying about the Gaussian beam first.
Yeah.
So for the Gaussian beam, if it is underfield, okay, then what will happen now? If it is perfectly filled, then you can see that entire part of this beam will flip this way. Basically, so you have like this, and this side beam will be like this one. So now if it is underfield, let's say, then your range will be small. So this is the range. Previously it was large. Here in this case, since in this case what will, it will be other way, because it's a ring is increasing, but the ring size goes down, and then it will have, that's why we are just entire power is dumped, that is what I said. So entire power is coming up. So here in the small domain, the intensity is high. So then, as I said, okay, you can just have a different combination of the input beam, and then you can get the structures or like that one. So I'll go to that one also. So far I talked about this scalar beam, scalar vortex beam, where polarization was not playing any role. Now vector vortex beam is something where you can just have this kind of polarization structure on top of the intensity distribution. Now the question is, nonlinear optics or nonlinear interaction doesn't really like the variation in polarization, so it cannot really just do that, okay? Because your phase matching is a polarization sensitive, so you cannot really just do that. So now the question comes, can you just make some mechanism or do some mechanism to generate vector vortex beam directly from the system? And if you want to do that, so we thought, let's do something like this. So we make a system, divide into two sections, section A and section B. Section A is the gain medium zone, which loves a particular polarization. So when the photon is or light is passing through this gain medium, we maintain the polarization state what it loves. So we'll just make that. And in that section B, we'll make all the polarization modification and modulation like this. So let's say if it is a linearly polarized light, it's going to that quarter wave plate circular polarization, left to right, then it will become vertical. Then when it is going through this one, it loves this horizontal one. So we are just now going with the vertical, so it will not do anything. So it will go through. Then again transformation is there, come back. So in every round trip, the beam comes back to its original polarization state and interact with the nonlinear crystal and generate. So that is what we devised. And that is basically, just we devised in this way in an OPO, where we can generate the vector vortex beam, something like this. So this is the OPO. We have pumped the OPO from both sides and modulate the polarization inside the cavity using quarter wave plates, 2 quarter wave plates in this. And then we try to see the polarization structure or generation of vector vortex beam directly from the system using in the signal. So when we are just trying to this pump, because I said the 2 pumps are there, 2 beams, say pump beam 1, pump beam 2, having the same vortex order, so that is confirmed. And we see that signal is having this shape or something in a donut kind of intensity distribution, which is also evident from the interference. And idler is always a Gaussian beam. And just to confirm whether it's a vector vortex beam, so we just made the polarization projection, because vector vortex is a superposition of polarization and OM mode. So if you just change the polarization, then the mode structure will be rotating in the Poincare sphere, higher order Poincare sphere. So you can see that one is there. Now the question might come perhaps that why it's so ugly, the intensity distribution. Because we are just dealing with nonlinear interaction, and then we are doing so many things inside the cavity, so and cavity doesn't really like it. So you have to somehow accommodate. So that's why we just try with the OPG. It's a nanosecond laser, so that you have sufficiently intense one. But the nanosecond laser also create OPG, optical parametric generation, that you cannot eliminate. So that's why some background is always there. Okay, so vortex beam somewhere, people use for various applications. Something, I love to show this one because this is one of the master students from ISET Pune who was visiting me and did. So I thought, okay, let's demonstrate this one. So people basically, just use vortex beam for this kind of fabrication. This is a nano fabrication, you can just see. And if you have to make such kind of pillars, it's an array of pillars, then you have to just go with the multiple sorts and a raster scan and so on and so forth. But we realize we can create such kind of structure in single shot if we design our input beam. So basically, just micro lens arrays are there where if you are this is basically the micro lens array structure you can see, and then which is defined with this kind of formula, where m is the parameter which depends upon the refractive index and the wavelength. Okay. So what we did, we just use this laser and then a micro lens array to transform a single beam into an array of beams, because micro lens array can just form that array. And then we just generate basically, just a micro lens array at 1064 looks like this. And then when you go to 532 nanometer, because wavelength is changed, then m has changed, and m has changed means it's, it's a delta function. These are the delta functions. If you just then the separation between the delta function will change. So that's why you just get that different kind of patterns coming out for different wavelengths. So by simply changing the wavelength, you can just change the spatial structure of the beam or the array. And when you do the nonlinear interaction of it, you just see some kind of structures like this. Okay. Then you can generate a single OM mode, but it's always nice to have a spectrum of it. So then we just try to see whether we can just generate a spectrum using a single SPP or not. So this is basically the design what we just use in the lab. Using a SPP 1 and 2, and then we just study the OM modes using these OM detectors for the signal, and then after the SHG also is nonlinear interaction, and then we try to study the OM structure of the beam. So as you can see, when you are going with that OM mode or vortex order 3, something like that one, which is also confirmed from this superposition of this LG modes or vortex beam order plus minus. So you will see such kind of lobes. And if you do the OM measurement, basically just seeing this OM content of the beam through phase flattening method, so you see that OM content, it is a pure OM mode. Now if you just keep on changing the position of this, let's say in the transverse direction, so you are just moving the spiral phase plate away from the beam. In that case, we start seeing some mode spectrum, something like this one. So you can just see that we started with 3, and then we are just getting that OM mode 1 and 2, where 3 is diminished. So in this way, you can just create OM modes. You can control the OM modes in case of pump beam, and then you can transfer also to the SHG beam, and then try to generate higher OM spectrum. And basically, this is useful when you are just doing this quantum optics experiment where OM modes are important. You can just simply use this kind of technique where you can just transfer that OM spectrum of the pump to the generated photons. Now, through this one, I'll just then we try to see something, just some experimental realization of the Hilbert Hotel. I don't know, many of you might be aware about this Hilbert Hotel. So this is something, just I love talking. So Hilbert Hotel paradox is something, let's say, if you have a grand hotel having infinite number of rooms, and all rooms are occupied. So fortunately, it's not the case for our case. So we have a single room, a nicely occupied one. So now you have a hotel which is fully occupied, and middle of the night, somebody come, new guest, and then say, I want to get a room. Can you just accommodate? In Hilbert in 1924, on his lecture, he said it's possible because you can just move first guest to the second to the fourth, n to n plus 1 number room. Since it's an infinite, countably infinite room, so your first room is vacant, you put that guest, so it's done. That's fine. Now the question is, can I just accommodate more? Can I accommodate infinite number of people in that infinite, countably infinite number of fully occupied hotel? That is possible also, you just transfer like that one. So this was there in 1924, he said in lecture. Then this George Gamow, in one of his book, 1, 2, 3 Infinity, where he nicely portrayed. And then people are just trying to see that, experimentally, can you just do that one? whether we can realize that kind of concept, or basically in the infinity is something, you know, always fascinate us. I mean, in childhood, we say, how many sands are there in the beach? It's infinity. How many hairs are there in infinity? Okay, so in 2016, this is basically, you know, just this is the concept. So in 2016, Greg Geber came with this idea. So he said that this can be realized in optics. So in quantum optics, people have just done something. So he said that using the fractional vortex, you can do that. So how? Let's say this is basically the image borrowed from his paper. So you have a beam. It's a vortex order 4.4. It's a fractional vortex. You can see it's a 4 charges are there, and then one dipole pair is there. And then if you keep on just changing this order, it's a 4.47, 4.5, like this, so then you can see the dipoles are forming. More dipoles are coming like this one. And this is basically infinitely extended. As if this is the room, this is a guest, this is the room, this is a guest, or something like that one, you can accommodate, okay? And it's infinite. Now, if you keep on increasing this fractional vortex order or fractionality or alpha parameter, then what will happen? So you are basically, you know, just going from 4.4 to 4.5, then you have created an infinite pair. Then if you further increase, then what will happen? So this one will heal, this one will heal, this one like this one. So it was generated like this pair. So always, you know, just dipoles are formed like this one, this pair, this pair. But when it's increasing, annihilation takes place in the other way. Basically, this one will annihilate with this like this one. So it starts from the infinity, comes back, and then they are basically, you know, just heal each other, leaving one there. So as if basically, you know, just you have accommodated this guest. So 4 was there, fully occupied initially, and then you are accommodating the 5th one. And like that, you can just keep on doing it whatever way you do. So basically, you know, you have to just use this fractional vortex. And then also he has just published another paper on this using Poincare beam. Now, we try to understand whether can you just do this kind of thing in experiments. So since we are just dealing with vortex beam, and can you do that one? So we have this SPP, spiral phase plate. We know that. And in case of spiral phase plate, that's orbital angular momentum is defined like this. So L is basically HS is the height, and refractive index difference between air and that material, it's a fixed, and then there's a lambda. So now we can see if we just change this wavelength, then the L is changed. So we can just change it. So if you just plot the topological charge for a vortex beam or let's say spiral phase plate, any spiral phase plate, and then if you keep on changing the wavelength, you will see that this topological charge is changing. And going all the way, sometimes it's a fraction also, sometimes it's integer also. So you can get all the things what we are just looking for. Okay, so then we just try to address, then I thought, okay, that's fine. And normally people just do, so they basically, you know, just make this kind of fractional charges using SLM, which is again, it's a difficult and control. So I was just thinking, we are thinking basically, you know, just use this SPP that we have in the lab, and then we need some wavelength tunability, and that we didn't have. Unfortunately, one day, one company came, tried to sell something to me. Then I said, can you just borrow something from you? I said, what? I said, I need a superconducting laser. Do you have? I said, yes, we have. Then give it. So that is what, you know, game started. So I borrowed a laser from a Dynotech. Basically, I should acknowledge them. Otherwise, I would not perhaps do this experiment. So they installed the laser for free. And that is what we start with the superconducting laser. And this is the experimental setup. And then basically, you're just doing the polarization, Stokes measurement, and vector state preparation, and so on and so forth. Because we can just do both the things, let's say, in a scalar vortex beam, fractional beam, and also the vector vortex beam. So as you can see, so now we start with a SPP fixed order, and then we keep on changing the wavelength. So here you can see it's a 2.8 is the order what we see for the SPP. I have not included all the images, but believe me, I have just selected only the images which will reflect the information or message I'm just trying to convey. So you can start with this basically just 2, 1, 1. So let's say this is the vortex order 2. But from the calculation, we find that it's a 2.8. And then we are just seeing some patterns coming on. So if you keep on increasing the wavelength, and when it comes to this 2.99, something like that, and you can see in both the sides, here and here, you will see that 4 patterns have appeared. And then this is basically the extracted phase. So here 1, 1. Now here is basically just formation is there. Then you can see at this case you have the dipole what I was showing from Professor Gever's paper. Then more things are there. So it's basically infinite number of dipoles are prepared or created. So if you keep on increasing this wavelength, so it's a 3 beyond 3, then you will see that exactly it's 4 has come. So we started with 2, it's coming 4, because this is basically here the SPP we have used is a two-step SPP. Two-step means basically it has, so it can be 1, something like that, and it's going 1, another 1. So that's why you have just 2. So using 2, you will go to 4 to 6 or something like that one. It will never go to 3. That's why that fractional vortex I am just saying at 3, because here it's just a 2 steps are there. That's why it's going. So as you can see here, now we have created this kind of dipoles series, and then they start annihilating and then landing only that 1. So we started with 2, we got 4, something like this one. So then we try to do using polarization singularity or vector beam, where we have just recorded the Stokes measurement here, and you can see also in this case these are the dipoles formed, and which is basically annihilating and then forming this kind of thing. So basically, just what theoretically he just predicted, that we are experimentally realizing that one can see the Hilbert-Hotel approximation or Hilbert-Hotel paradox, that experimentally using OM beam one can realize. Another thing is basically everybody know this kind of Young's double slit experiment, where we start with incident beam, and then a double slit is there, interference pattern looks like. But the condition is, both the inputs or the sources S1 and S2 should have the same polarization state. And if you see this intensity pattern here, basically you will just see the intensity pattern is varying something like this depending upon the position, and we see that bright and dark. Now the question is, let's say if you just make this orthogonal polarization states for these two, let's say this one is vertical and this one is horizontal, so we will not see any interference. That is what just from class 12 standard we know. But Professor Nirmal Viswanathan is there, so he said no, there is something else. Even though you have orthogonal polarization state, you should see interference, but you should not look at the intensity. That is what basically just you have a vortex beam of order L and B polarized, and horizontal Gaussian beam with a horizontal polarization, and if you mix them, interfere them, this is what you get in the polarization degree of freedom. So there is a pattern in the polarization degree of freedom, and what we get like this. Now if this beam goes, this is basically called full Poincare beam. This beam is having actually all the polarization states on the Poincare sphere that can carry. So basically just some coverage is there, we can calculate. So this is basically the polarization structure of the input beam, and if it passes through this axicon, again the Bessel beam, interesting thing happens. Basically it will create an infinite series. So since I was just talking about the infinity, so let's see the infinity, because Bessel beam is infinitely extended, and in this case we will have this kind of beam, we will have lemon and star singularity. So it's a lemon and star, and when it passes through the axicon, we will have, because basically lemon and star, the conservation will be there. The number of lemons should be equal to the number of star, and when it passes through the axicon, it forms an infinite number of lemon and infinite number of star. So since we have that, we thought, okay, let's do the Hilbert-Hotel paradox or something like this one, because we have just created infinity, and Bessel beam is having its self-healing property, so you can just block and see study its self-healing property. So then is it possible to do that? That is how, just 1 year back we thought of, implementing the Hilbert-Hotel paradox. And basically, as I said, you can see this is the polarization map. C points is a star, and lemons will be just infinitely extended. And now you can just always say that stars are the guest and lemons are the hotel rooms, and then fully occupied because it's a conservation. And if you see in 10, say 5 Stokes phase 512, you will be seeing again the same kind of structure what I just talking about, the infinite one. And then we just try to understand whether self-healing property is maintained or not. So this is the intensity pattern of this Poincare beam, Poincare vessel beam. And then if you are just blocking it, it's basically self-healed after a certain time, if you're just seeing this one exactly. And perhaps, I don't know whether you can see. So the intensity, whatever you just blocked, basically, just going out. So here it has come to this one here, and then finally it's going out of the frame. So basically, just intensity from outside ring will come to the inside, and then you form that vessel beam back. And we try to understand whether when we are blocking the beam, whether we see any change in the polarization states or not. Basically, here you can see, so I'll take a. And as you can see from these images, the degree of polarization for all the beams remains unchanged, even after block also. So without block, whatever that pattern looks like, so it's almost the same. So that means when you are blocking the vessel beam, you are not basically reducing its polarization degree or degree of polarization of this one. Then we try to see whether it's really working in that way Hilbert's paradox was there. So here without block, this is a Stokes phase we have just plotted, or ellipse orientation. Basically, it's ellipse orientation. You can see this and this is each ring is having a pair, always on either side. When you block, to create that dissimilarity in the number of lemon and star, and that is what we have just created. And then we let it go, we see funny things are happening. And after certain distance, it's almost healed. So whatever number was there, so the number is coming. So not like the way Hilbert predicted, like it's because you can see from the intensity pattern, the intensity was coming from the back, and then the dark was going out. We are hoping that that will happen, but it never happens. That is very strange. So what is happening, when we have just block here, it's creating this, due to the diffraction, it creates infinite dipoles. And these dipoles will replace the old dipoles and form the new structure. So after propagation, you can see exactly the same beam we are getting back, whatever we started with after the block is coming back, but it has just gone through different things. So just to appreciate that one what it is, so basically we have just we have just marked it spots. So black spots and white spots are there. Now you can see we have just created after the block is one extra. So the rest of the other same, black and white is the same, only extra, just to create that Hilbert new guest has come or new room is there, something like that one. Then after a certain distance propagation, we are just studying. Basically, we are just creating these open dots, open circles are there, black. So these are the newly formed dipoles, which will basically, after a certain distance, is basically at this distance we have conservation is satisfied. So it's not like that just this has gone and then it's just a numbers is changing. So we see basically, just same number coming back and then new dots are coming. So whatever we initially started with is basically a newly formed dipoles. That we are just trying to understand, and then Professor Geber is also doing the simulation. His simulation is exactly telling that same thing what we are seeing, but it's not Hilbert kind of thing, but it's basically just a new infinite series, manipulation of new infinite series. Means how it's happening, nobody really know or understand. Yes, sir.
Does this evolution in the in-between distances, do they have a pattern? Do they
Yeah, actually they go here and there, that is why basically from the theoretical simulation you can just go finer and then see. Basically you can see it's just dipoles are there. So these dipoles will be just, this one will go and eat this one, something like this one. So it's basically evolving in very dramatic way, and that we cannot really just.
I'm asking, so only simulation will tell whether if there is any evolution pattern.
No, it's not happening. In the simulation also it's not happening.
It is random.
No, random means after the diffraction we have series, infinite series. So up to this point, this is a conserved. Entire thing is conserved. So we are expecting that when the self-healing is there, this movement should be there. But it's not happening. So from the diffraction, perhaps it's an infinite number of dipoles are there, which is annihilating and creating a new pattern. So means he is also struggling to find out why it's happening. It's so difficult to understand why it's happening. But it's a Hilbert-like kind of thing. So you started with a pattern, you block, you got something. But it's a different infinite number of series you can just think of. Okay, so I'll just go to the last section because I think I have already put many people in sleep. I'll wake them up because T is there. So here is that imaging in sphere characterization of single photon. So we just talked about this high power, high number of photons, but now let's go to the single photon and then see how they behave. So this is basically the experimental setup with this single photon experiment. This is a clumsy one because 4 experiments are there in the single go. So we start with a pump beam at blue wavelength and then generate a pair photon as a single photon using this PPKT crystal, periodical pole crystal, and we divide it. First we see that whether the single photons are really single photon or not. For that we do this HOM interferometry by taking these photons and then passing through, and then they are interfering and delaying one with respect to the other one and seeing whether we have the variation in the coincidence counts. Then what we do, we just image the intensity distribution of the beam while changing the intensity distribution of the pump, if we just keep on changing, and then seeing the photon, single photon. So for that, we have to just delay these photons by single photon delayed by, let's say, 30 meters or something like that in free space. It's propagating and then coming to the CCD camera, ICCD camera, which is triggered by the detector. So one of the detector is here, which triggers that one for this imaging experiment. And then what we do also is just try to interfere the photons, single photon, which is being generated. Yes, sir. Yes, sir.
Your home,
Yes, sir.
you have this counter-propagating beams, right? These 2 beams are falling on the
Beam splitter.
right?
Yes.
Now this, how are you getting the delay? One beam you are getting delay.
Yes, this one. We are just delaying. So
These long ones, N5 and
So first, let's say if you are just doing this experiment, then the one photon goes like this, comes back here. Another photon is tapped here,
okay,
going here and falling here.
right.
So in the beam splitter, then we are just delaying one photon with respect to the other one,
Oh, I see.
and then seeing the coincidence.
What is the role of this N9?
No, this is another experiment to see the imaging. So first we do this, then stop. We remove this this mirror. Then the photon comes here, it gets delayed, and it comes back, again comes here. So one photon goes here, another photon goes through this delay and comes back here. So this delay is something 30 to accommodate the delay for this ICCD electronic delay, something around just 30 nanosecond or so. So you have to just accommodate that. So that basically is a triggered ICCD. Just when it sees one photon, then it asks this camera to open so that the partner can be detected. Otherwise, it will not open. So it's just a coincidence kind of imaging.
You can tune that tau.
Yes. Yeah. And then when we are doing this interference, then we again flip this beam from here, and then it's a Mach Zehnder interferometer with a delay, and then do the ICCD and then image it with respect to this photon. So one photon is always going to this, other photon is coming through this one and going here for imaging. Second is for interference, many things. So you can just choose which way you want to go for this experiment. So to see this HOM interferometry, that is what is that plot you can see. It's a reasonably good visibility for that interference, and as expected, the interference visibility goes down because we are just pumping hard. Let's say 15 milliwatt is the power, so then the beam intensity basically just creating other photons or so. Whether then counts, maximum counts, full width maximum something around 1 millimeter, close to that one we are getting because of this narrow line width of the generated photons. Then what we did, we basically just changed the spatial structure of the pump beam here. This is the pump beam. We use pump beam of different vortex orders, and which is basically confirmed using these tilted lens images. So you can see the counts and then see that this is the order of the vortex. And we see the same intensity distribution for the, so when we just see the imaging of the single photon with that coincidence imaging, so you can see with that order, it's the lobe structure is or the donut shape size of the donut is increasing, which is also confirmed from the tilted lens saying that what is the order of the vortex. That means basically just we have this pump beam having vortex order 1, and signal we are or one of the photon which is projected in the Gaussian mode. It says 0 order. That means according to the conservation law, this pump has to be transferred to this photon, so other photon. Otherwise, its conservation is not will be violated. So in that case, we see that one is a pump photon wave mode, or the spatial structure is.
How do you know whether